Welcome back to High Performance Computing Advanced Scientific Computing course. This is lecture 10. We will talk about the OpenFoam software and CFD application. This is a short recap that in the lecture 4.2, which we had planned to have a workshop from VScale Cloud Computing. We had some practical example from OpenFoam software. In this lecture, we will have a detailed discussion about the decomposition, and also we'll look at some practical example from OpenFoam on the Elia system at the University of Iceland. Base of the outline, this is lecture 10, OpenFoam software and CFD application. Since this year we promised the HPC course will be specialized for the CFD application. So far we had many examples and discussion regarding the high performance computing resources in the CFD application. Let's go on the lecture 10. Let's have a review from the lecture 9. In lecture 9 it was CFD and parallel computing. We had example from the fluid flow, especially in the turbulent flow, from the nature, from the industry, from many different applications. And we visualize the difference between the laminar and turbulence flow. We mentioned that turbulence flow is a three-dimensional phenomenon, so it's necessary to simulate these kind of flow in the 3D, which make it much more difficult, and it required HPC resources. We looked at the available methods from the computational fluid dynamic for turbulent flow, Reynolds average Navier-Stokes RANS, large eddy simulation LES, direct numerical simulation DNS. We had examples from these three main categories. RANS usually used in the industry, and it's provide average solution. When we are using the LES, the accuracy higher than RANS, but it's much expensive than RANS. Based off the literature and some studies, they made comparison for the same cases of the CFD. LES around 10 to 5 times costly than a RANS method. The next one is the DNS, which is provide about exact solution. We saw from some statement, for example, Reynolds for his experiment used the DNS to calibrate the hot wire, so we can understand how much the DNS is close to the experimental condition. Then we saw some difference between the RANS and the LES for some example. Then we had a very short review on the topology, which is required when we are doing the CFD with HPC resources. We take a look on the static and dynamic categories, and the topology that's available in these two categories. In the next part, we looked at the parallel computing with the MPI and how the decomposition is running between different processors. What is the general structure of the code when we are using the MPI, and how it's helped to have a speed up on the solution. Then we had some turbulence example with RANs, LES as DNS, and some comparison regarding the cost and also regarding the speed up. And some drawback available in the RANs. For example, for RANs, for a case was with change of the geometry, RANs did not get the change of the geometry, and so this is one of the drawback on this approach. We recognize in some cases we need to use LES or DNS to calibrate the solution of the RANs to make it in the better accuracy. Also, we saw when we are using the DNS, it capture all the scale that they are available in the flow from very small to large scale, and we saw them in some example. Also, we looked on the example with 3.9 million element, which we were looking at the performance efficiency. Then the idea was if we use better solver or we're using high order solution or more parallelism. And when we look on the parallelism, especially we found it sometimes increasing the number of the processor does not help too much to get speed up and faster solution. So there are many required item to be put together that must be put together to have a proper solution. Also, we point to shortly n sub half, which is available in the solution of the CFD when we have time step. And we saw with the example that the GPU make the speed up effectively higher with increased number of the GPUs. Now let's move on in the lecture 10. The outline of the lecture 10, we will have two parts. Part 1 will focus on the OpenFoam and MPI, and then in the second part we will talk about the running parallel. In the first one, we will look on the environment of the OpenFoam, the decomposition method, MPI and decomposition, and the domain decomposition. Then in the second part, we will look on the boundary condition when we are using MPI domain. We look on the boundary condition, which could be periodic and non-periodic. And also we have some practical example from the decomposition on the OpenFoam. So for first part, this is the environment of the OpenFoam. You see this example from the OpenFoam. It's open source code, so it's free and it's could be modified for the new cases. It's cover the problem in the laminar regime, in turbulent regime, and also for compressible and incompressible, and possible to run it on the parallel computing on the cluster, and also on the personal computer like laptop. However, it's relevant to the power computing power of the system. Regarding its language, it's C++ toolbox, and it's capable to customize numerical solver. It has a pre and post-processing utility and solving the continuum mechanics problem. One of them, computational flight dynamics, CFD. And it's applicable in many industries: automotive, manufacturing, process engineering, and environment engineering. One of the important part in the setup when we are running the OpenFoam in the parallel, it's the decomposition of mesh, which we need to choose the method of the decomposition, and also how many sub domain will be available in the decomposition. We will look in detail on this part of the OpenFoam. Regarding the structure of the software, It has a directories, and we need to make the setup. Also about the visualization, it's use PowerView, and we can visualize the solution. As you can see here, the window of the uh, PowerView and how the setup on it, and we can use it to look at the result of the simulation. In the example we will run on the second part, you will see this uh, visualization of the OpenFoam and how it's working. Regarding the library and directories, OpenFoam is a simulation configured by several plain text input. They are located in the system, constant, and zero, and in each of them has a these libraries which control dict and others, and also about the constant, and also about the zero, which usually focus on the initial time directory. Also, it's possible for processing to convert data to VTK format and visualize them on the PowerView. These information most practically, you will see them in the cases that we will run on the second part of this lecture. And here it's presenting the PowerView, which is a software for the visualization, and it's possible to run it on the desktop and HPC resources, and it's also open source software. It's free to download, and also you can use it on other software. For example, I know some people with Python programming also using the PowerView for the visualization. Regarding the parallel computing, here is a simple example for the domain decomposition. When we want to run the problem in parallel in the CFD, especially in the OpenFoam, we use the MPI capability. In this regard, we decompose the domain of the problem. Here we can see this domain is decomposed to 6 subdomain, and each subdomain is specified for one processor, processor 1 to 6. One point it's the overlap between each subdomain. There is an overlap which here we can see, for example, when we look at the processor 1 and processor 2, where is the overlap, and it's necessary to swap the boundary data in this overlap. When we have a 3D dimension, this will be much more complex, and it's necessary to pay attention to these boundary data, because in the end, when we solve the problem for every subdomain, it will be reconstruct and gather the information for all domain. So it's necessary to be synchronization between the boundaries of the subdomains. Regarding the memory, also you can see this calculation here. If we assume for this domain we have 20,000 by 20,000, the storage requirement will be around 6.4 gigabyte, which is for this simple problem is showing the memory is too high. So if we assume for the 3D model and more complex problem, how much memory will be, it's necessary to have enough memory to run this kind of a simulation. Here is an example from the lead-driven cavity flow, which one of the well-known cases in the OpenFoam, and it's presenting the difference between the speed up with the MPI library. The figure in the left-hand side shows a single node scalability test on 200 times 200 times 200 cells meshes. We can see both the MPI and the MPI plus OpenMP implementation deviate considerably from the ideal scaling performance when using more than 4 cores. And indeed, the best performance of the hybrid codes result to be 10% slower than the best performance of the pure MPI codes, based on the result which presented in this figure. And in the another evaluation, in the right hand side, the figure presenting again the MPI application with multiple nodes. Also, the number of the meshes get lower. It's 100 times 100 times 100 cell mesh on the multiple node. As expected, the best performance, which happened on 29 seconds, obtained by the hybrid code, which is 20% faster than the best pure MPI run, which was at 36 seconds. And it's located on the place that double the number of the cores. So this is indeed the benchmarking, which consider the scalability of the MPI application, and it's very clear on these two both figures. We can see the difference between the MPI and ideal scaling when using the single node, and with multiple node it has a very close area between the ideal and MPI for a specific number of the cores. When they're going up, the difference is getting considerable. As we said in the OpenFoam, the decomposition methods are available, and in the running the case in parallel, we can set up the appropriate model based of the problem. Each of these methods has some feature. For example, the simple one is a geometric decomposition, which the domain is split into places by direction. Two pieces in the x direction, one in the y direction. The another one is hierarchical. It's again geometric decomposition, which is the same as simple, except the user specify the order in which the direction split is done. It didn't specify that must be on the x and y, and should be specified by the user. The S-coach is the another decomposition which requires no geometric input from the user, and attempts to minimize the number of processor boundaries. The user can specify a weighting for a decomposition between processors. So the S-coach is working different and is not based on the geometric of the subdomains. The another one is the manual. The manual decomposition, where the user desirably specify allocation of each cell to a particular processor. These four methods are most used approach for decomposing OpenFoam, and you can see based of the desired method of the user and the capability of the solution, we can set up the decomposition method and run the simulation. As an example, here in this slide, I am showing you a batch file for OpenFoam for parallel run, which we will run it practically in second part on the Elia system. All of you have access to the system, and I will share this batch file with you to run your assignment. Of course, the first part of the batch you should know about them after these few assignments you have been done. You know, firstly you need to specify your user and choose the partition. Then you need to specify the number of the node, task per node, and also you can choose the specify the memory per CPU. If the partition has a GPU, also you need to add the setup. The maximum time for the running, you can specify it here, And also you can have an output and error file to see how the running was going during the submission. This setup for the OpenFoam actually is depend to the version of the OpenFoam, and also there are some other different library need to be considered. Here, this batch file setup is for the area. Maybe if we work with another cluster, we need to have some change on it. Firstly, the directory created for this simulation, and then the required module is loaded, which is, as you can see here, is an OpenFoam on the MPI. Then the source form batches need to be run on the bin file to work with this batch. Again, you need to have the case from the OpenFoam. Here, since this is the example to see how the parallel working, we are taking a copy of the case from the OpenFoam tutorials, and we're using it here. If you make your case, this section is not required, and only you need to address the directory of your case. Then one important thing is the decompose predict setup, which here we are doing the setup. You need here to specify the method. We said we have simple, hierarchical, scotch, and manual. When you specify the method, also you need to write the number of the subdomain. The number of the subdomain should be equal to number of the parser that here in the batch file you specify. This is very important. If not, you will get error during the running. Then after this setup and specifying the number of the subdomain and the method of the decomposition, you can start to run the OpenFoam simulation. Is starting with the meshing, create a mesh, and then decompose par will make the decomposition of the domain of the problem, and then you can run the model with this parallel setup, and you can see the result. In the next, in the part 2 of this lecture, we will have a practical example, and you will see how you can run the OpenFoam in parallel, and also visualize its result by Power View. Regarding the Power View, there are two options. If it's installed on the cluster, with the command of the Power View, you can run the Power View and visualize the result. If it's not installed, you can make some setup with the connection and some information from the port of the cluster, and get access to the result, and with running the Power View from your desktop, visualize the result. All of these information, we will see them in the practical part, and you will be able to run this simulation in your system. So far, we talked about the OpenFoam and its capability to run it in parallel. We can summarize its capability for the decomposition on the MPI. Since we know the OpenFoam, it's a computation flight dynamics toolbox, allows the parallel computation of flight dynamics simulation on a theoretically unlimited number of the processor core. Indeed, it's a software that utilizes a message passing interface MPI library in order to facilitate communication between parallel processes as the computation is completed. In order to maximize the parallel efficiency of the computation, the way in which the MPI application distributes the problem among the processor need to be optimized. Based off these description, we can say the decomposition also need to cover some condition to be successful to run parallel. Here in this slide, you can see example of the decomposition for a block. First, the question is what the domain decomposition. First, it's a parallel method, and then the domain portion are assigned to individual processor. If we look here on this example, it's a block, and it's divided to 8 small blocks, each block assigned to one processor. It's also the form of the subdomain. It's depend of the shape of the problem domain and also about the geometry. For example, we see in the right hand side again this domain divided to 8 block, which each block has a column, and again each column it's assigned to one processor. These present that the decomposition also has a relevance with the geometry of the domain, which need to take into consideration. Here again also we see the decomposition for the same domain use another shape of the block. It's a slice in the horizontal form, and there are 8 blocks. We call them as slices, and each slice is assigned to one processor. So here we have this group, and based on the shape, we presented 3 type of the possibility to decompose this domain. If we want to summarize the domain decomposition steps, first we need to break up the domain into blocks, which we call them subdomain, and assign each subdomain to MPI processor 1 to 1. Then write or modify the code and only update it for a single block or single subdomain. Then it's necessary to provide a map of neighbors to each processor and insert the communication subroutine calls where is needed. Then adjust the boundary condition of the code. As an example, in the right hand side, it's presenting a domain of the problem and how it's divided to 4 subdomain with a specified coordinate. And in the second figure, it's show how it's assigned for each processor from number 1 to 4, 1 to 3, because the processor started with number 0, 1, 2, and 3. And this shortly display how we can make the decomposition of the domain. However, in this lecture, we will run the decomposition on the OpenFoam. OpenFoam has this command and the structure to make the decomposition, and we will practically see how we make it on a specific CFD domain. Here we have finished the first part of the lecture 10, OpenFoam software and CFD application. There is a video here which describing the message passing interface, MPI, and how its utilization could help to get speed up in the parallel computing. I suggest you to watch this video. Its link is available on the reference of the course, on the lecture. And in the part 2, we will have a boundary condition for the MPI setup when we have the physical boundaries for the subdomain. And after short description about the boundary condition, we will have practical application of the OpenFoam based off the MPI and how we can make the setup to run this kind of the cases. So we will continue in the part 2 and thank you.